In this lesson, we're going to continue what we were talking about or what you observed in the video about the Exxon oil spill that happened in Alaska back in 1989. And a couple things that we might want to pull out just from reading this passage is a couple of things that, the amount of millions of gallons of oil that were spilled, how much that area that needed to be cleaned up. We also know that initially there was relatively simple and inexpensive techniques, and then later on the most intensive and cost intensive techniques were used by using this manual cleaning process. And so we have a function that will allow us to better understand how much was, or what the cost was. So this is our output, the cost, and that cost in billions of dollars. And our input is P, and that represents the percentage of the oil damage, or the percent of the oil that's been actually cleaned up. So um, so those cleanup efforts. So just we want to fill in the table, and so if we go to Desmos, and then we're going to kind of answer these questions A, B, and C here based on what we come up with in our table. So one thing with our table, so f of x or c of x, again, x being the input variable, equals, now an easy way to do the fraction is just to hit the divide key first. So when we hit the divide key or the slash key, it'll give us a fraction there, so we can easily make sure that we have a numerator and a denominator. And you'll note right away that rational functions are a little bit different than any function we've looked at already. And in this case, it does have a numerator and a denominator. A rational number, so anytime we're working with rational numbers, a rational number by definition is a fraction that, when converted to a decimal, will terminate or repeat. So the most famous irrational number would be pi, because pi does not ever end, nor does it ever repeat itself. So pi is an irrational number. E is an irrational number. The square root of 2 is also an irrational number, but these two are the most famous irrational numbers. So if we go back to Desmos, we want to create a table. So we're going to go to the gear, select the table, and we're going to change our table based on the input values that are given or the percentages that were given. And we'll note that when we get to 100%, we have undefined. So filling in this table, our outputs, and we can just round to 2 decimal places to make it easier for us. So 0.02, 0.05, 0.12, 0.32, and then for 100% we end up with undefined. And so describe the behavior of this table. Is it increasing or decreasing? How is it doing this, and at what rate? So we can see that as the inputs increase, the outputs are also increasing. So this is an increasing table, so it's increasing. Now, if it was increasing linearly, we would know these are increasing by the same amount each time. So are these increasing by the same billions of dollars? And so here we have $0.03 billion, but here we have $0.07 billion. So it is not linear. So it's increasing, but not linear. Now we would have to divide these. So 0.05 divided by 0.03. And then we would compare that with 0.12 divided by 0.32 to decide whether it's exponential. And we can see here that in this first set of ordered pairs, we are 2.5 times. So if I multiply 2 times 2.5, I'll get the 5. And then from 5 to 12, if I multiply 5 times 2.5, I get about 12. But from 12 to 32, again, just ignoring the decimals because they're in the same place. So this is actually 3 times. So it's closer to exponential, but not truly exponential. Okay, so we have an idea that this is growing pretty fast. It grows kind of slower at first and then grows fast. And then why is this behavior appropriate? Well, again, if we look back at our reading, we notice that this first one only 20 and 40%. So this is those less expensive techniques. And then it got really expensive because this was a lot more time consuming. So these were the time consuming techniques. All right, so then for part B, we want to look at why do we get this C of 100 is undefined? And so when 100% of cleanup happens, we get an undefined cost. And we want this in both mathematical and contextual terms. So if we look at the mathematical terms, so mathematical, and we plug in 100, so when we calculate C of 100, that means we get 0.08 times 100 over 100 minus 100. Well, we know that on the top we're going to end up with 8 over 0. And we know that nothing can be divided by 0. And so 0 this forces this to be undefined. Because division by 0 is impossible. Okay, so if we look at contextually, well, contextually, as the percentage increases, so again, this is an increasing table, as the percentage of our cleanup increases, and we get closer and closer to 100%, the cost becomes a lot more expensive. So, so there's really two reasonings, or we know that because this is at 100%, so the contextual reasoning for why we get 100%. So the input is 100%. So at 100% cleanup, again, we need an input part of our statement and an output part of our statement. So at the 100%, we get an undefined cost. So it's not necessarily that the cost is undefined, but the cost becomes so expensive the company no longer can pay for it. And this is this idea of an asymptote. Okay, so we're going to talk about both horizontal and vertical asymptotes with rational functions.